never be sure about. Okay, so then how to solve this problem? So this analysis of infinite horizon bargaining game is way more complicated, or way more challenging. So I'm not gonna give you every details, but I just give you some sketch. Okay, so how to tackle this problem. And if you are interested in details, then I also describe a little bit of details in the supplementary note as well. And if you still learn more, you can ask me for some reference. Okay. So actually, one of author of our main reference, Ariel Rubinstein. So he is the one of authors of one of textbook we are using this semester. One of textbook was written by Osborne and Rubinstein. And that Rubinstein is actually the guy who actually developed this theory, infinite horizon bargaining game. So if you like, I can give you reference, which paper of his you have to do. Okay, so what is general? So I just give you again, I'm not really gonna give you the full details, but describe how to attack this problem. Okay. So there can be possibly infinitely many subgame perfect equilibria. Okay. However, you can always order this possibly many multiple subgame perfect equilibria in terms of what is the payoff, equilibrium payoff of the first proposal. Okay. If I give you any subgame perfect equilibrium of this game, then you can simulate that strategy profile, and you can check what is the proposer's equilibrium payoff in equilibrium, right? And if I give you another equilibrium strategy, then you can also calculate again, what is the equilibrium payoff of the first proposer in that equilibrium. Okay, and in principle, two different equilibria result in different payoff for the first proposal. Right? Player one will enjoy possibly different payoff in different equilibria. Okay. However, if you order all those equilibria in terms of player one's equilibrium payoff, then clearly there will be maximum payoff player one or first proposer can enjoy in some equilibria, and there is also the minimum, the least payoff that player one can enjoy in some equilibria. Okay? So if there is, for example, if there are only two equilibria, then there are actually only 2 points in this comparison. You can, let's say, just for example, let's say player one's equilibrium payoff in one equilibrium is 0.6, and player one's equilibrium payoff in another equilibrium is 0.4. Then the maximum payoff for player one is 0.6, and the minimum payoff is 0.4. Okay, and if there is 3 equilibria, you can do the same thing to order 3 equilibria in terms of player one's payoff. And even if there are infinitely many equilibria, in principle you can do that. Anyway, what is important here is there should be a maximum payoff that player one can obtain in some equilibria, and the least payoff that player one can obtain, or more precisely speaking, first proposer can obtain in some equilibrium. Okay? And let's call B bar, that is the highest payoff of the first proposer, and B underbar, that is the minimum payoff. Okay? And also you can do the same thing for the first responder. You can also think of what is the maximum payoff that the first responder can obtain in some equilibrium, and there should be some least payoff, the minimum payoff, such that player 2 or the first responder can enjoy it in some equilibrium. Okay? And let's call this maximum payoff W bar and this least payoff W underbar. Okay? Okay, so this is how to attack, and then given that B underbar, B bar, W bar, W underbar, this is the way we can tackle this problem. Okay, so choose one subgame perfect equilibrium. Okay, just choose and fix one subgame equilibrium, and let's think about what has to be happening in that equilibrium. Okay, so remember, notice here that there can be possibly infinitely many equilibria, but we just choose one and study what happens in that equilibrium. Okay? Then again, suppose two players fail to reach any agreement in the first two periods. Okay? So they fail to reach any agreement in the first period. So they move on to the second period. Again, even in the second period, they fail to reach any agreement. So they reach to the third period. Okay, so here is the crucial part of moment here. Okay, if you think about what happens in the third period and afterward, so in the third period, player 1 makes an offer, right? It is odd period, so it is player 1's turn to make an offer. And player 2 will accept or reject. And if player 2 rejects, then they move on to the fourth period. But if you think about what happens, if you really carefully think, the subgame beginning from the third period is exactly identical to the entire game. Okay? The entire game has infinite periods beginning from player 1's turn. And the subgame we are talking about is it also has infinitely many periods, again beginning from the player 1's turn. Okay? So this is crucial observation here. And that kind of thing never happens for the case with finite horizon, right? If you think about finite horizon bargaining game, subgame beginning from period 1 is just simply different from the subgame beginning from period 3 because the number of periods are different. But this is the case, but here two subgames are exactly identical because factor T is infinite. Okay, then you can, let's say gamma 1 is payoff of player 1 in the subgame beginning from period 3, and gamma 2 is player 2's payoff beginning from period 3. Okay? Then gamma 1 has to be between these two numbers, right? So remember that V bar, this number is the highest payoff that the first proposer can obtain, right? And B underbar is the lowest payoff that first proposer obtained, right? And if you think about the bargaining game, subgame beginning from the period 3, then player 1 is the first proposer. So gamma 1, his payoff has to be in this set, in this interval. And the other player's payoff, gamma 2, also has to be in this interval. Okay? Okay, then about, if you think about the entire game again, then it is just 2 periods. Mathematically, it is equivalent to the 2 period bargaining game with arbitration process at the end of second period. And the payoff from the arbitration process is gamma 1 for player 1 and gamma 2 for player 2. Right? Okay? So then we know how to solve that problem. Okay? So the unique sub-game perfective equilibrium for 2 period bargaining game with arbitration process, the outcome depends on, of course, gamma 1 and gamma 2. Okay? So actually, player 1's payoff in that game is so in 2 periods bargaining game with arbitration, we know that, using the same backward induction idea, you can show that in equilibrium, player 1's payoff is going to be 1 minus delta gamma 1. Okay? So so this is something you can calculate. This is not really obvious, but you can solve this number using backward induction. Okay? So gamma 1 is the payoff of player 1 if they go to the arbitration process at the end of second period. Okay? And then it is simply equals to, there should be that. So it is simply equal to 1 minus delta plus delta squared gamma 1. Okay? So if you fix gamma 1, any gamma 1, you can solve what is player 1's equilibrium payoff. And if you look at this formula, so how to get this formula, you can do it by yourself, or I'm not really sure whether I include it in the supplementary note, but actually this game is kind of the game you can easily solve by yourself. So anyway, so you can see that player 1's payoff is increasing in gamma 1, right? Which is kind of natural, right? If I have better gamma 1, then my payoff in the entire game has to be increasing. But in particular, this is minimized when gamma 1 is B on the bar, and maximized if gamma 1 is B bar, right? Gamma 1 has to be between B on the bar and B bar. So, okay, so then, however, this entire game, payoff you want, also has to be between B bar and B on the bar, right? Remember that B on the bar and B bar, they are maximum and minimum payoff that player 1 can get in any equilibrium, right? So U1 has to be also in that interval. So which means that U1 is minimized when gamma 1 is B on the bar, and that number has to be equal to B on the bar. Okay, so left hand here is U1 on the board, and minimized by plugging gamma 1 equal to B on the bar. And the maximum payoff of player 1 is player 1's payoff is maximized if gamma 1 is B bar. So you have to have this inequality here. Then actually, using this inequality, you can see actually you can derive that actually B on the bar and B bar has to be equal with each other, which is 1 over 1 plus delta. Okay? And similarly, you can also, in the similar way, you can show that B low bar and B bar is also the same which is given on the slide. Okay, so this is complicated one. So let me summarize one more time. So if you have anything unclear yet, just stop me and ask. Okay, so the crucial observation here is, if you think about soft game beginning from third period is just identical to the entire game. Okay, that is the crucial observation here. Okay, and if you think about what happens there, player 1's payoff, which is written as denoted by gamma 1 on the slide, has to be between V on the bar and V bar. The lowest payoff of player 1 and the highest payoff of player 1 for the entire game. And if you think about player 2's payoff, gamma 2, that is also has to be between W bar and W on the bar. Okay? So that is our second observation. And then the next thing is, okay, so we already know, so fix gamma 1 and gamma 2. Okay? Then fixing gamma 1 and gamma 2, we fix what happens in third period and onward, afterward, if they fail reach any agreement in the first two periods, right? If they fail reach any agreement in the first two periods, they will get gamma 1 and gamma 2. Okay? So formally speaking or mathematically speaking, that makes the entire game two-period bargaining game with arbitration process. Okay? And you can solve what is equilibrium outcome for that game, two-period game with arbitration process. As gamma 1 and gamma 2, gamma 1 and gamma 2 are payoffs from arbitration process. Okay? And then if you solve that equilibrium, which has to be unique, you will find out that U1 is increasing in gamma 1. Okay? You will also find out that U2 is also increasing in gamma 2. And which means that U1 is the maximum. U1 becomes maximum when gamma 1 is V bar, right? But U1 itself is also have to be equal to V bar in that case. We are using the exact identity between the entire game and the sub game. Okay? So that results in this inequality. So if you work with this inequality, you can, it's just kind of high school algebra. So you can find out that two numbers have to be identical. So the last part is just mechanical algebra. But what is important idea is there are two important ideas, game theoretic ideas. Identity between the entire game and the sub game begins with the third period. Okay, and transformation every entire game into the two-period bargaining game with arbitration. Okay. Okay, so that the last conclusion here on the slide tells us that actually there is unique sub-game property equilibrium actually, right? So the minimum payoff of the player 1 and the maximum payoff, two numbers are actually equal with each other. So essentially there is unique equilibrium. Okay? So actually you can prove, this is not really easy to prove, but this is proven by Rubinstein, back in '82. So he actually, using this idea, he actually could show that in the alternating offer bargaining game with infinite horizon, he could prove that there is actually unique sub-game property equilibrium. And in that unique sub-game property equilibrium, player 1 offers this thing in every period, in every odd period, and player 2 offers this thing in every even period. Okay? So these are strategy, two-dimensional strategy. Whenever they have to, they can make an offer. In other case, in every even period, player 1 accepts ST as player 2's offer if this offer is larger than this fraction. And player 2 also accepts player 1's offer in every odd period, if player 1's offer is less than. So basically, this is just full description of equilibrium strategy profile. And if you work with this strategy profile, you can see that actually in the first period, player 1 makes an offer this 1 minus 1 over 1 plus delta, and player 2 will accept this immediately. Okay? So I don't really want to go into too much details beyond this, but hopefully, I successfully gave you some idea of how to tackle this problem. And this is the result. Okay? So one nice thing, so here is one last comment here. So we have solved the case with t finite and t infinite. Okay? So we didn't really talk about all details for the case with the infinite horizon, but in principle we know how to do it. And then we have some general proposition, adapted from Rubinstein's paper, 82. Then the last question is, okay, so what happens if t goes infinity here in this formula? And you can ask whether this formula approaches to the formula here. And if you check that actually as t goes to infinity, this term goes to 0, right? And this term also goes to 0. So these two formula, 1 over 1 plus delta and delta over 1 plus delta, that actually indeed converges to this formula. Okay? So as you increase the number of periods more and more, it approaches to the case where t is exactly infinite. Okay? So that is something worth to look here. Okay, there's one more comment. Okay, so sometimes people are interested in what happens, as delta goes to 1. What does that mean? So if remember delta is discounting factor, right? So if delta increases, that means there are two cases that delta will increase. First, delta will increase when players become more patient, right? Or alternatively, delta also increases even though there is no change in players' patience. Let's say the real time between two offers shrinks. Okay? Consider the case that, so in period 1 and period 2, it takes, there should be some time, right? They have to, they need some time to finish period 1 and finish period 2, right? So there is some real time they have to finish their game in each period, right? So if that real time is longer, then discounting factor has to be smaller. Okay? And if that real time length of each period is shorter, then that means discounting factor has to be larger, right? So even if there is no change in terms of players' patience, if real time length of each period becomes smaller and smaller, delta will go to 1. Okay? So why does it matter? So, shrinking of real time length of each period, that can be interpreted as, you can interpret that as, vanishing any friction in bargaining process, right? So the reason we have some time to finish each period, that comes from any friction in bargaining process, right? So maybe, if you negotiate with some emails, that, for example, then there should be a lot of friction, right? Because you sent an email writing down your offer, then you have to wait a little bit, right? So then in that case, delta has to be smaller. But okay, so then you can think of the case that as the technology improves, then there's such a friction will have to vanish, right? So then delta will go to 1. So some people are particularly interested in that case. What happens if we have perfect bargaining technology so that there is no friction at all in terms of exchanging our offer? Then what is interesting? That case is interesting. That answer for that question is interesting because if delta goes to 1, you can see this number goes to 1/2, and this number goes to also 1/2. Okay, so whatever difference between player 1 and player 2's share in equilibrium, that comes from some friction, technological friction in exchanging their offers. Okay, and this difference will be vanished, will be 0 as friction disappears. Okay, so this is kind of good thing because it means that our analysis here actually kind of matches our intuition. What is our intuition? Intuition says that if there is no friction in terms of bargaining technology, then there is no really, the kind of intuitively right bargaining outcome has to be half and half, 50 and 50, right? So indeed, that's the case here. As delta goes to 1, bargaining outcome, equilibrium outcome converges to 50 and 50. Okay, any question? Okay, so let me wrap up what we have done here. So I just gave you some class of bargaining games. Okay, so there are actually 2 classes of bargaining games here. So finite T and infinite T. Okay, and both of them, in terms of bargaining rule, both of them employ alternating offer bargaining game. Okay. So here is kind of main takeaways of this lecture. First of all, this lecture provide you some natural bargaining rule, right? Alternating offer bargaining game, and show you what is the equilibrium outcome. You can take it as a kind of game theoretic prediction for any, for this kind of bargaining situation. Okay, so that's the first takeaway. In alternating offer bargaining game, which is kind of natural in many cases, then outcome has to be such and such. That's one takeaway. And the other takeaway is, of course, in different situations, you will observe different bargaining rules, right? I mean, sometimes the seller makes an offer all the time, and buyer only can answer. Sometimes the seller and the role of proposer and responder will be determined randomly, right? So, for example, we can think of the bargaining model such that in every period, either player 1 or player 2 will be selected randomly as proposer with some probability, right? So there are tons of different bargaining rules you can think of, but probably in many cases, you can analyze different bargaining situations, basically similar technique here. Okay? So the second takeaway of this lecture is, I kind of try to provide you some techniques, illustrate some techniques you can use whenever you want to analyze bargaining situation with game theory. Okay? So I believe some of you are already beginning, what to present for, student presentation and, what is your potential topic for your, final report. right? Then remember that final report is basically about real world application of game theory, right? You choose one possible application, real world application of game theory, and analyze it and present at the end of the semester, and also write down your report. Okay, and then if in the course of your research, possibly you have to think about what is maybe your application is related to some bargaining situation, right? So your topic may include some bargaining component. Then first thing you have to do is which kind of bargaining rule is observed in your case. Okay? Then you write down some model. Sometimes you can just directly use this model, or sometimes you have to modify it a little bit, right? Then, however, even if your model is not exactly identical, possibly you can apply the same technique to solve your bargaining case. And if you find whatever interesting, then you can present it at the end of semester. So game theory is kind of a tool. I mean, whatever I present to you in this lecture, you can think of, you have to think of these things as some illustration of game theory as a tool. Okay? In different application, you have to modify models slightly, and you have to analyze by yourself. Okay? Any question? Okay, then let's take a break until 7:35. So it's gonna be 15 minutes break. Okay?